Hello everyone. Our project's name is Design and Simulation of a Custom Controlled Pick and Place Robotic Arm using X-arm robot. Uh, we did not implement the part of the pick and place. Basically, when we are not able to show how the robot is picking an object and placing it to another, but we are able to design the custom path planning using our idea. So so those who are not from the domain, let me tell you about the big picture of our project. Uh, um, so this one is an exam robot. So imagine you have a robotic arm like a mechanical hand sitting in front of you. You tell it, I want to move it from point A to point B. Like this one is point A, the starting point is point A, and you want to move it to this direction. This one is point B. The robot does not automatically know how to get from point A to point B. It's like trying to drive a car across a city where you have never visited. um, so our project aims to create a map and route for the robotic hand or arm or joint, whatever you think. The goal is to figure out a smooth path from the starting position to the final position, making sure the robot does not bump into anything along the way. Once we have the route, we convert it into the instruction of the robot's joints because robot takes the input in terms of the joints. Uh, and it can move according to the joint input and output. So uh, let me talk about what was before implementing our project. For example, we have to for example to get this the project done, we have to install a lot of libraries. Like we have installed the uh, operating system ROS Humble. We have installed necessary packages like Move It, which helps to know how the robotic arms moves. We have installed the Gazebo and RBs packages, which are useful for the visualization. Like like this one is RVs and this one is Gazebo. In the Gazebo, you can see how the robot looks like in in physical condition. Um, for example, I have moved this robot from this point to this point. I can plan and execute. Yeah, now this robot is moving from this point to this point. You can see. Uh, so who makes this path planning? So by default, the Move It package has the path planning uh, thing, and using this path planning, the robot is moving right now. But our goal is that we will move the robot using our own created path planning algorithm, not using from the Move It package. So for this we have used the path planning algorithm, that is RRT and A star. RRT is a rapidly exploring random trees. You can think of dropping random dots all around the space where the robot can reach. We connect those like you connect these dots until you form a tree that hopefully leads from point A to point B, like exploring a city by taking random turns but keeping track where you have been. The A style on the other side, the A style algorithm will help you to find the best possible route from point A to point B. And after the path planning, we have uh, uh, we have used the knowledge of inverse kinematics, which will tell the each joint of the robot arm what angle to turn, so the hand actually gets to those positions. Inverse kinematics is the math that figures out how the bend is joint to make the arm's hand reach in a certain point. And after obtaining the inverse kinematics, when we have all the joint angles of the each step of the journey, we send this instruction to robot's internal controllers or drivers, which move the motors and make the arm move smoothly along the chosen path. So let me talk about the implementation little bit. Like I have shown you how the robot is moving using the move it package. Let's make it. Let's make it to the home. By the way, when it will go to the home, you can see from the end effector position that the position of X, Y, Z, and also the orientation. Now this will go to the home. Okay. Uh, this is the source code of our project, and let's talk about the source code a little bit. Uh, from the first, yes, these things are these instruction are used for imports and some setup, and we are taking the input like XYZ role p chow, uh, and this one is the default. We are also taking the inputs from the user, and this one is the start position. We are thinking like the start position, and also we have created the ROS node in the RT planner named robot motion planning node, and we also creating the bound which defines the range of values allowed for each dimension. This helps the RT know where it can sample points, and another important instruction is this one, this line. This RRT star first builds the tree of sampled states using RRT. Once it can connect to the goal or is close enough, it uses the A star search to refine the path through the sample nodes. Parameters like step size, max iteration, goal threshold, goal bias control the RRT's behavior and accuracy. And we have also created the IK service client. The code waits until the compute IK service is ready. We are using this service from the move it package. Once available, it will be used to convert Cartesian poses along. Uh, once available means the once the service is available, it will be used to convert Cartesian poses along the path into corresponding robots joint angles. And if the path is found successfully generated, each state in the path is sent to the IK solver. The resulting joint angles for each waypoints are saved also. And sending our results into the move group. Yeah, this one here. We are sending our results into the move group. After the IK solution are obtained, we use an action client to send these joint states to move action server. Move group actions tries to execute the plan on the physical robot. And when we are done, we are shutting down. We're also using lot of helper functions like angle distance or at a star search, Euler to quaternion, which converts the role PCO into a quaternion for the IK requests. And compute IK service also convert the part to join states and send goal, which sends the final joint state goals to move group action server to move the robot arm. Okay, so let's give an example of our code. For example, our goal is to reach the end effector to this XYZ and roll PCO. We are giving this command and we will see the robot will move there. Yes, this one has been moved here. And you can check, yes, the XYZ and roll PCO is pretty much the same. You can also see this one also in gazebo. And you can use whatever goal point you have, you will just give give the input as xyz and roll PCO, then the robot will move. uh let's talk about the success and failure of our project. The success point is our code is working and successfully our code is working, and uh, the robot is moving to our destination. But obviously there are some failures also. To be honest, we did not understand what is the failure. Today when I was talking with Dr. Vikas, then I figured out something like we did not use the collision check. Basically, the problem is like we did not understand it properly. We thought when we saw the service of the computer key, it has one request parameter like avoid collisions is equal to true. We thought it will check the avoid collision, but this is not right because the RTN style algorithm in this code sample only consider the distance and feasibility in terms of geometric configurations. They do not use any collision checking function to verify whether the sample state or the transitions between them are free of obstacles. In other words, the generated path might pass through areas where the robot would collide with something, but the code does not detect or prevent this. Uh, what we used basically when the code requests the IK solutions from the computer IK service, it sets the uh, avoid collisions parameter is equal to true. This instructs the move IT IK solver to try to find joint angles that do not collide with robot's own body or known obstacles. So the known obstacles are not sent by the RRT of our code, but basically it will not collide with its self body. So self collision is automatically checked by the move IT service. If the IK solver cannot find a collision free solution for a particular waypoint, it will fail that request. This can help ensure that the final joint configurations along the path are collision free, but it does not guarantee that the planned Cartesian path itself avoids areas where that are unreachable or inherently in collision. Uh, throughout this though there are some failures, but throughout this project we have learned a lot about the robotics basics and how this one works in complex system. So thank you, Dr. Vikas, for introducing this course.